You know, in chemistry, we often face this needle in a haystack problem. It's a huge deal when you need to make sure our water is safe to drink or our food is nutritious. Well, today, we're diving into a really powerful technique that's designed to do just that: complexometric titration.
All right, so here's the central puzzle we're tackling. Just imagine you've got this sample of water, and you have to know exactly how much lead is in it. But, of course, the lead isn't just sitting there by itself. Nope, it's swimming around with magnesium, zinc, and who knows what else. So how do you zero in on and measure just that one thing with incredible accuracy? That is the exact problem we're going to solve today.
And the answer is a technique called complexometric titration. At its heart, it's all about using one molecule, called a ligand, to find and form a special colored bond with the specific metal we're hunting for. This new little structure is called a complex. And the magic happens when every last bit of that metal has formed a complex. A sharp color change suddenly tells us, hey, you've hit the endpoint. It's what allows for a super precise measure.
Now, to make all this happen, we need a special kind of tool. So let me introduce you to the absolute star of our show, a molecule called EDTA. This thing is the chemist's secret weapon for this kind of analysis, and believe me, it's for a very good reason.
See, you could use simpler molecules, or ligands, and they kind of get the job done. But they often form weak bonds, they react in these messy, multiple steps, and they give you this blurry, gradual, hard-to-read result. But then there's EDTA. It's what's known as a multidentate ligand, which is a fancy way of saying you can think of it as having multiple arms. It just reaches out and grabs onto a metal ion, forming a super strong, really stable bond in one single clean step. This perfect one-to-one reaction is what gives us that sharp, crystal-clear endpoint. It's literally the difference between a blurry, out-of-focus photo and a super sharp, high-definition.
All right, so we've got our super tool EDTA. How do we actually use it? Well, the most straightforward method is called direct titration. And honestly, in a perfect world, this is the only approach you would ever need. Think of it like a journey in 3 parts. First, in the pre-equivalence phase, you've got way more metal ions than EDTA. Then you hit the critical moment, the equivalence point. This is the sweet spot. You've added just enough EDTA to bind with every single metal ion, and bam, a sharp color change signals you've arrived. If you keep going past that point, you're just adding extra leftover EDTA. That color change, that's our destination.
But, you know, chemistry isn't always ideal. It rarely is, actually. So what happens when your reaction is just painfully slow? Or what if you just can't find an indicator that gives you that nice, sharp color change? Well, in that case, the direct approach completely fails. So chemists had to get a little bit clever.
And for these exact situations, chemists developed a really clever workaround. It just requires a completely different strategy. You have to start thinking in reverse. Instead of measuring what you're using as you go, you measure what you didn't use at the end. It's a technique called a back titration.
Okay, so here's how it works. First, you deliberately add a known excess amount of EDTA, way more than you actually need. Then you just wait. You let that slow reaction go to completion. Finally, you measure how much EDTA was left over by using a different, fast-reacting metal. By subtracting those leftovers from the amount you started with, you know exactly how much EDTA reacted with your original target. It's a brilliantly simple solution to a tricky problem.
Okay, so we can handle slow reactions. That's a great trick to have. But what about our original problem? That messy mixture with multiple metals all jumbled together. This is where the real advanced puzzle solving begins. See, the big problem here is what we call interference. EDTA is awesome, but it's not perfectly selective. It'll react with the lead you want to measure, sure, but it might also react with the zinc and magnesium floating around in that same sample. This creates a kind of chemical noise that just completely ruins your results.
So how in the world do you silence that chemical noise? Well, the solution is it's brilliant. You use a tool called a masking agent. And the best way to think of it is like a pair of noise-canceling headphones, but for your chemical solution.
These masking agents are amazing. They are specifically designed to go in and selectively grab onto those interfering ions, the noise, and just hold onto them tight. By forming a stable complex with them, they essentially make those ions invisible to the EDTA. It's like they're telling the EDTA, hey, ignore these guys over here, they're not what you're looking for. This lets the EDTA focus only on the metal you actually want to measure. And the coolest part? Later on, you can add something called a demasking agent to release that ion if you decide you want to measure it too.
All right, let's see all this in action. We're going to follow a real analysis, almost like a chemical detective story, to figure out the exact amount of lead, magnesium, and zinc, all in a single messy sample.
Okay, let's follow the clues. First, the chemist puts those headphones on the zinc by adding cyanide, which completely masks it. With the zinc silenced, they titrate with EDTA to get a combined total for the lead and magnesium. Next, to isolate just the lead, they add an agent called BAL. Now, BAL binds to lead even more strongly than EDTA, so it effectively steals the lead away. Now we know the lead amount, and we can figure out the magnesium by subtraction. Finally, they remove the headphones from the zinc using formaldehyde and titrate that now free zinc with EDTA to find out how much of it there is. It's a beautiful multi-step process.
Now, EDTA is clearly the MVP here, right? But it's important to know it's not the only tool in the box. Let's take a quick peek beyond EDTA.
For instance, there's the classic Liebig method. This is a non-EDTA titration that's used to measure cyanide. Here, you use silver nitrate, and instead of a color change, your endpoint is signaled by the entire solution suddenly turning cloudy as a solid forms. It's just a great reminder that the core principle of forming a complex can be applied with all sorts of different chemical tools.
So, let's recap the essential tools in your new Complexometric titration toolkit. You've got EDTA as your all-star player, perfect for its strong, clean, one-to-one reactions. You have direct titration for all the straightforward jobs. You've got back titration as your clever workaround for those tricky situations. And you have masking agents as your high-tech solution for noisy, complex mixtures. When you combine these techniques, you empower chemists to solve almost any analytical puzzle that gets thrown their way.
So, I'll leave you with this final thought. Now that you understand the logic of this incredibly powerful toolkit, from direct measurement to thinking backward to silencing chemical noise, what complex chemical mysteries out there do you think could be solved next?